Okay, our last presenter for today is David Fritz from SLAC, and he will be he's the head of facility development, right?
Yep.
And he'll be talking about LCLS II and some of the things we can expect from that once that comes online.
Great, thanks, Phil. The microphone that's recording, is that
it's on here, right? Yeah.
Okay.
That one's for the room.
Okay, perfect. I'll try to just speak loud for everyone. So first, I just wanted to acknowledge our funding agency, the U.S. Department of Energy Office of Science. Also, speaking on behalf of a lot of people, in particular the LCLS staff as well as the LCLS II project teams. And that includes a lot of partner laboratories that are helping us with this large construction project. I'd also like to thank the organizers for inviting me and giving me the opportunity to share some of the excitement with LCLS II with you. Hopefully get you guys excited as well. So just quickly, just wanted to jump to the point. So what is LCLS II? And so LCLS II, basically we're replacing 1/3 of the SLAC Accelerator, which is a warm technology, with what we'll call a CW superconducting accelerator.
Where's LCLS I on this slide?
It's not on it.
Where would it be?
It will be way over here.
Further downstream.
Further downstream. I have a picture that'll show that better. But I wanted to focus on what are the beam parameters that this new accelerator would bring to us. And actually, before I do that, let me just, I think our nomenclature hasn't been so good with LCLS II, because a lot of people think it's a brand new facility and replacing LCLS. Actually, it's just augmenting LCLS. So we still maintain what we have with LCLS now. We're not getting rid of our current accelerator. It's just we're able to choose which accelerator we use to feed into the different FEL sources. So I just created a table here that shows a few parameters just to cross compare. So with LCLS today, we go down to about 250 EV, which gets us to the carbon K edge, all the way up to, we've extended the energy about to 12.8 kV to get it to the selenium K edge. That's, with that accelerator structure, it operates at 120 Hertz. It's a very bright electron beam, and we can get very high energy electron beam, and we can get on the order of 4 millijoules per pulse, somewhat routinely these days. And when you look at the average number of, the total number of photons per second, it's about 10 to the 14. With LCLS II, of course, we can still feed that copper accelerator, the difference being that we're installing new undulator systems. That allows us to extend the photon energy range of the hard X-ray undulator. But we can also feed that source into the soft X-ray undulator, which has a larger period. And what we get from that is actually, we kind of get close to that 10 millijoule range, Marius, what you were talking about, which is pretty exciting, I think, for the single particle folks. Of course, the big advancement is with feeding the superconducting source into these undulators. And there, the photon energy is somewhat limited on the hard X-ray undulator just due to the limited electron beam energy. But the repetition rate goes up to about almost 1 megahertz. And that beam isn't quite as bright, so the per pulse energy is not as high as the copper accelerator. But the big gain is with the average number of photons per second. So just to provide some context, I think we've already heard a lot of, there's a nice presentation on the compact source that kind of went through the FEL physics. Basically, briefly on one slide, there's 3 main components. There's the electron gun, there's the accelerator, and there's the undulator. And with free electron lasers, there's sort of two configurations. You can have sort of a low gain oscillator configuration where you have mirrors that bounce the light back and forth. And you just have an output coupling mirror that lets through a portion of the beam. That works well for wavelengths that are much longer than X-rays. I think with X-rays, although there is a concept for creating such a cavity on the X-ray wavelength, it's rather challenging. And so the method of choice is to go with a very long undulator and do this all in a single gain high pass amplifier. And so that's why you've seen already many pictures of these very long undulator systems that have to be precisely aligned. SLAC has been around for a long time. It's a 3 kilometer accelerator. And if everything's kind of running in full blast, then all the sections were connected as they were, roughly a decade ago, we could actually produce a 50 GeV electron beam, which is pretty high energy and a high brightness beam. And that's a big ingredient that's needed to create an X-ray free electron laser. And for that reason, this was chosen as a site to build LCLS, and that's probably one of the only reasons why this facility turned on in 2009 and compared to some of the other facilities that came in later, that there's a lot of existing infrastructure in place. We didn't have to wait for modulators and things like that. That's delaying the Swissville startup. So in 2009, we started user operations. We were configured to have initially 6 experimental end stations. We've recently added a 7th end station, an additional instrument in the far hall. In this configuration, roughly 2 of the instruments are dedicated for soft X-ray operation, and the remainder are dedicated to hard X-ray operation. And as was mentioned earlier, we do have a bit of a gap between the high end of the soft X-ray instruments and the low end of the hard X-ray instruments in this so-called tender range, which is sometimes problematic for us. So we've been running for 5 years, or a little bit more than that for now, and we believe that LCLS has done pretty well. This plot here just kind of shows a couple different metrics that our funding agency likes to look at: their publications and the number of users. And so in both areas, we've had sort of a steady increase over the years. Roughly almost 700 papers have been written so far, and we've done roughly 350 experiments to date. So when you actually compare those ratios, it's actually pretty good. In terms of the number of users, again, you see that the number keeps going up. We had roughly 800 users, unique users, on-site users last year. And recently, just a couple months ago, we had a review article come out in the Review of Modern Physics, and that kind of summarizes the sort of early science results in the first 5 years of operation. So I encourage you to have a look at that if you're interested in having a nice summary. So everything's been going well, but of course things aren't perfect. In particular, with this type of accelerator structure and technology, and as well as the spontaneous process, the Sassi process that we're using, the FEL beam has a lot of fluctuations in it. And so this is in sort of every parameter you can imagine. It fluctuates spatially. You can see the beam jittering around. It fluctuates in intensity. You see this color scale, each pulse jumping in and out. It fluctuates in spectrum, and it fluctuates in time. So this plot here just shows basically what you need to know is that edge is a measurement of the relative arrival time of an optical laser with respect to the X-ray beam. You see all these parameters fluctuating, and they fluctuate significantly enough that each pulse basically has to be diagnosed individually. So and that can be a limiting factor for many experiments. We do expect things to kind of improve significantly with a quote-unquote CW machine, but and we've done our best actually to correct for some of these fluctuations. And a particular success story is for the pump probe measurements, where with these online diagnostics measuring this arrival time for each pulse, you can actually sort your data based on that arrival time. So although you can't control it, you can measure it. And this plot just kind of shows how powerful how much of an improvement that can make. So basically, it's just a measurement of a solid that's been pumped with an optical laser, and so without reorganizing the data based on this diagnostic, this is the plot that you see. But once you do this reorganization, that's actually the result. And so now you can see these coherent lattice vibrations in the solid. You can see the signal to noise is very good. And so this is what we can do today. But taking things to the next level, a CW accelerator. And what we mean by CW is that the electric field, RF fields inside the accelerator structures are always on. It's not like a continuous source of X-rays, though. That still comes in pulses. And so it's just a question of how many pulses you want to feed into these accelerating structures. And we're taking an approach where we think we can fill about 1 megahertz worth of bunches.
CW, that means that the X-ray pulses are equally spaced.
Yes. Or we can choose to drop pulses. Basically, we can make an arbitrary pattern.
Incredibly misleading term.
CW is for that's for the RF field inside the cavities,
Most people don't know that, but
right.
It sounds like it's a plane.
Right. So it's referring to the accelerator structure, and I agree. That's why I take time to try to explain it whenever I give this presentation. So, this plot kind of summarizes. This is the average brightness. So most of the curves that the FELs like to show are the peak brightness, because that takes into account the short pulse duration, and that's a big chunk of the 10 orders of magnitude that you see in those plots. But in terms of average brightness, you can see we weren't, LCLS, the FELs weren't particularly different from the storage ring sources. And in fact, with the multi-band achromat sources, we were going to be lagging behind by about an order of magnitude or two. With this upgrade, you can see this boosts us up sort of 4 orders of magnitude in average brightness. And of course, that allows us to do different types of experiments than what we can do today. So for example, in the field of atomic and molecular physics, there's coincidence measurements that need to be done in sort of a single photon limit. And that does not lend itself well to good statistics when you're just at 120 hertz. And so those type of experiments, coincidence spectroscopy, we can now use, as well as there's a lot of advanced spectroscopies that just are very photon starved. And for example, resonant inelastic X-ray scattering are 2 examples that are shown here, one in a chemical system solution, the other on a correlated material, a solid state material. These measurements, ultimately you want to make these 2-dimensional maps, and you want to make them for various pump probe time points. Today, we've demonstrated that such measurements can be done in LCLS, but more or less an entire experiment during that time, we can get maybe 2 or 3 time points, and that's about it. With this increase in average brightness, all of a sudden you can make a full map and potentially even change more parameters. So that's the gist of it. but also not to be ignored is, with this sort of CW accelerator, that allows you to actually, really feed back on the stability of those fields at a very high frequency, high bandwidth. And that should significantly improve the stability of the beam compared to what we have today. So John here is going to your map. There's the entire SLAC aerial view. So LCLS today, we inject, actually it's this portion here. That is the 3-kilometer SLAC accelerator. So LCLS today injects at the 2/3 point, accelerates up to about 15 GeV in that kilometer. Then there's just the electron drift region, undulator hall, and then the 2 experimental halls connected by an X-ray transport line. And LCLS II will use the 1st kilometer, and we'll build an electron bypass, and then a crossover point where then we'll have magnets that can switch either the superconducting beam into the undulators or the copper beam into the undulators, or a combination of one in one undulator and another in the other.
There's 2 undulators.
There's 2 undulators, yes. So what's new in terms of infrastructure and equipment? It's, obviously we have these 2 new undulators. Today we only have 1 fixed gap undulator. The new superconducting accelerator, as well as the cryogenics plant to actually cool that accelerator to just a few degrees Kelvin. So just comparing the 2 technologies. So LCLS-1 again uses normal conducting technology, what we'll call warm, and LCLS-2 uses superconducting technology, what we'll call cold. And so they have slightly different RF frequencies. The average gradient of the copper structure is higher than that of the superconducting structure. And because of that, and as well as this, we're only filling roughly 700 meters of that kilometer we're clearing out with superconducting structures, and the gradient's lower. This is why the electron beam energies are so different. But the big difference between the 2 technologies is, the warm technology, you introduce a microwave pulse into the cavity, and that this cavity is relatively low Q, so that the duration that field is on is roughly about 1 microsecond. And again, that gets pulsed at about 120 hertz. With the superconducting source, it's a very high Q, and so at the rate that we pulse it, it just kind of stays energized all the time. So it's CW, we can stuff roughly close to 1 million pulses in there in a second. So the meat of the project is the cryo modules, and these are leverage all the development that has gone on at the EU XFEL and in Hamburg. We have some slight modifications to this cavity to allow for CW operation. These cryo modules are being fabricated at partner laboratories, Fermilab and Jefferson Lab, and we have a couple prototypes that have been assembled, and we're currently testing them, and we'll continue to test those prototypes over the coming months. Within those cryo modules, there's these 9-cell cavities, and as I showed on the previous slide, what was assumed in the LCLS-2 design to get to 4 GeV was a gradient of about 16 megavolts per meter, with a Q of roughly 1 times 10 to the 10. And we've fabricated, roughly a dozen or so of these cavities, and have tested them. And the early results are pretty good. So on average, we're seeing a Q that exceeds our specification, a gradient that actually exceeds our specification. So hopefully, of course, these things have to be assembled into a string together in a whole cryo module, and we're anxiously awaiting how that goes. There's lots of ways for this to go wrong, but if we can kind of maintain that performance, then we'll be in good shape, and we might be able to push to even higher energies than the current 5 keV limit. We're going with two different undulator systems. The sort of vertical gap, horizontal polarizing undulator is going to be installed on the soft X-ray branch line, and on the hard X-ray branch line, we're installing a vertical gap, horizontally polarized undulator. So we'll get a vertically polarized beam coming out of the hard X-ray line. I think the key difference is that, again, both are variable gaps, so we'll be able to tune the FEL over a much wider range than we currently can today. It gives us a lot of flexibility. Just a few pictures of the current status of things. So this is just a picture of the Klystron Gallery in the first kilometer. You can see that basically it's all, I don't have a before and after picture, but basically this is all cleared out, whereas before it was filled with lots of things. And that work has happened actually pretty recently, over the past month or two. And now we've kind of disconnected the power that's going to the actual accelerator tunnel down here, and now work has begun to remove all those that accelerator hardware to clear it out for installation of the cryo modules. Okay, now moving on to end station development. So this is the configuration we envision we're working towards with LCLS II. So currently, again, today we have 7 instruments that are fed by a single undulator. In our planning for LCLS II, things are going to change a bit. And so the far haul basically stays constant, but we'll be making a lot of modifications to the near haul. And so what you'll notice is that we'll basically take out the first 2 instruments and install new instruments in those areas. And then we also modify the hall itself, and we'll deflect beam up to the 2nd floor and install 2 additional instruments there. So when everything kind of shakes out, you'll have these 2 undulators. The soft X-ray undulator will feed 4 instruments. The hard X-ray undulator will feed 6 instruments, and basically we'll have 3 soft X-ray instruments, 5 hard X-ray instruments, and then we'll fill the gap that we have today with a tender instrument. And I think for this audience, probably people are pretty familiar with working in CXI and MFX as well as AMO. However, in this new plan, I'll go into a little bit more detail for these 2 instruments here, because I think those are going to be the 2 that are most relevant for the science that people in this room are going after. So basically, those 2 instruments are high flux instruments. So the design philosophy is to kind of preserve as many photons as we can to bring to the sample. That's done by minimizing the number of X-ray optics. And also, there's no monochrometers or things like that that really cut down on the flux. One thing that I forgot to mention, and let me just kind of take one step back. With this tender instrument, you'll kind of notice that it can be fed by either undulator source, and that's either individually or simultaneously. Simultaneous option's kind of interesting for these nonlinear optics experiments, but I'm sure people can also probably think of interesting experiments where you're simultaneously doing diffraction and soft X-ray spectroscopy simultaneously. Anyway, so in both of these instruments, we're looking to have some fairly small foci. So 1 micron focus in this tender instrument, as well as a 1 micron focus in this sort of new version of AMO. There will actually be an additional focusing system on the AMO line that will get us somewhere between 300 nanometers up to maybe 600 nanometers, depending on the photon energy range. Upstairs, that's where we deflect the monochromatic instruments, and so we're looking to have a variable resolution monochromator that can go up to a pretty high resolving power. So in the sort of a new version of AMO, this is just sort of like a conceptual rendering at the moment. We're still in the early phases of the design. But basically, for sort of coherent scattering and imaging, that will still occur in the lamp end station, and that'll be with this 1 micron focus. And I think the main difference is that we cut out a lot of the upstream mirrors that we currently have today, and as well as we're using much larger mirrors. We should do a much better job of collecting all the photons that are created. So I think in practice, the photon density that we'll realize with this instrument should be an order of magnitude above I would say the commissioning version of AMO before we experience degradation of our mirrors. I think today it's kind of a question mark what the photon density we see today after 5 years of operating. With this tender instrument, as you can see, it's basically a very similar instrument to the CXI instrument in the far hall, with the exception that you have this raft that kind of tilts to point, either at the soft X-ray undulator. This is kind of the configuration you would want to be in if you are interested in 10 millijoule pulses at 120 hertz to do imaging. However, if you're doing crystallography and maybe you're more interested in collecting data, 20 times or 50 times faster to try to, maybe do pump probe experiments to get more time points, and you might not need that extra factor of 4 or 5 in per pulse energy. You would point at the hard X-ray undulator, and we could run the machine at whatever repetition rate our detectors we can read out at. So initially, we're thinking, and this is somewhat open for discussion, but we're aiming for something between like a 4 to 8 kilohertz detector readout rate. And this is just the conceptual rendering of that instrument now. And so as you can see, this is not too advanced, and which means that it's really important for everyone here to kind of, this is the time where your input can really influence the design of these instruments. I think, 6 months from now, 8 months from now, we're kind of going to be ballistic. And if we're going to have these instruments on the floor in time for first light, we have to kind of freeze the design and start sending drawings to the shops for parts to be made. And so we set up sort of a website, and you can kind of get links to this website in multiple ways from the LCLS home screen. And there's email addresses that send that actually get distributed to the design teams for these 4 end stations. And it would really be great if you guys could visit that website, and there's a lot more details about the instruments there. And please send us your thoughts. This is the right time to do that. If you don't have time to do that, there's another forum to get your input and get your voices heard, and that's at the upcoming LCLS users meeting. So this will be held in early October. And this is just the chart showing the 4 days of the users meeting. And in the first day, we have a full day workshop on these new instruments. We're going to be splitting up at some point in the day to split the monochromatic instruments from the high high flux instruments. And so we encourage you to attend and get all your experience and design knowledge into these new instruments. In terms of project schedule and sort of user run schedule, so we're in a little bit of a trickier, I wouldn't say trickier, but it's a fairly complicated situation where we have a running user facility, and at the same time we're trying to do a major upgrade. So this is just the calendar here over the next 4 or 5 years. We've split this chart into 2 rows where you have the hard X-ray undulator and the soft X-ray undulator. Of course, until currently it's just one undulator system, so everywhere you see blue, it's the same. This isn't split up into 2, but down here it is. So what you'll notice is that we're running today. We're about in the middle, sort of towards the tail end of run 13. We have another user run that takes us through this calendar year, and then sort of in the mid-December we shut down. And we shut down for 6 months. We come back on in June, run for a year, and then we shut down for a longer period. This is a full year shutdown, and it's in this period where the new undulator systems will be installed. Of course, we're fortunate where we can still run all during this time, even as the superconducting accelerator is installed because of just the separation geographically. We initially turn on with the copper accelerator feeding the hard X-ray undulator, and then it's sort of in 2020 when we start commissioning and bringing up the superconducting accelerator. And this is this is a gradual turn on. So I think in the first few months it'll start just sort of at a few kilohertz, and then beam will get ramped up, and it's about 1 or 1.5 years before the full machine capabilities are realized. Another thing just to point out is obviously we have it's the same staff that are operating our instruments that are developing the new instruments, and a lot of our engineering resources and technical resources are being will be redirected to developing those instruments. So we put a very big focus on efficiency and to try to sort of gain time from people to be able to have those developments happen. And so maybe you have noticed this already, but we've started a standard configuration program where in the beginning of LCLS, we would kind of do a lot of gymnastics with each of the instruments. We'd change setups around week to week, and that's great from sort of a flexibility standpoint, but that's not great in terms of the demands on our staff if we're going to have to design new instruments. So we've been operating in sort of a slightly different mode, and the rationale, the reasoning for that is to be able to be ready, to have instruments ready when we turn on in this time.
When does run 17 start?
So basically, this purple would be run 17. That would be limited to just the hard X-ray line and with the copper accelerator, but it would be with the variable gap undulator. And then we'd probably have a run 18, which would be in this time period. And that would be the first time the superconducting accelerator would be available. In terms of access and proposal guidelines, so similar to what Raphael said, LCLS is a general user facility. There's a Department of Energy definition of what this means and sort of the guidelines for it. And I just pulled 2 of those out that I think are relevant. So, LCLS it's open to all interested users without regard to nationalities or affiliation. And we don't, there's no user fees that are charged for non-proprietary work, as long as the intent is to publish the results in the open literature. Proposals are submitted for a single experiment. We don't have program proposals. These proposals are ranked by a proposal review panel. Currently we have 7 sub-panels that are broken out into different fields. I would say the primary criteria are scientific merit, originality, and the need to use LCLS. And in parallel to that, that effort, the proposals also undergo a feasibility screening by the LCLS instrument staff. Sometimes users will propose things that are kind of beyond the capability of what we can offer. Beam time formally is awarded by the LCLS director, but it's with strong advisement from the proposal review panel and the feasibility review. And I think it's it's almost always, with just a few rare exceptions, the proposals just are allocated beam time directly from the PRP ranking. And typically, we award beam time in any number of shifts, typically normally ranging between 1 and 5 12-hour shifts. Oh, and sorry, one more. And so this is our current process, and it will remain the same for LCLS II. Okay, now future upgrades. And in particular, I'd like to discuss a proposal that's being prepared called LCLS II HE. So as you saw from the Slack site, the overview I gave, LCLS I uses the last kilometer, LCLS II kind of uses most of the first kilometer, and then there's more accelerator in between. And so, and there's also lots of other real estate on the Slack site to steer the beam. We're not in the forest, so we have a lot of possibilities. In particular, if we actually fill out that whole first kilometer with additional cryo modules, we're able to achieve about an 8 GeV electron beam energy. This would allow us to reach the selenium edge at high repetition rate. Or if you actually fill out the entire second kilometer with superconducting modules as well, that would allow us to get to about the 18 GeV CW accelerator. An alternate option would be, rather than extending the superconducting accelerator, you actually connect these 2 copper accelerators. And there's 2 possibilities there. If we stick to 120 Hertz repetition rate, we could increase the electron beam energy to about 24 GeV, which would be pretty high energy. Or currently the way the accelerating modules work is that the RF pulse that's created by the Klystrons actually gets stacked. And that allows a higher amplitude but shorter duration pulse. If that was, stacking was undone, we could actually run the accelerator at 360 Hertz with the current electron beam energy. Additional improvements could come from, with the superconducting source at the higher photon energies. It turns out we're very much emittance limited. And by improving the emittance of the electron beam, that would extend the photon energy up to 20 keV or so. Alternatively, you can install superconducting undulators, and that would allow more per pulse energy to come out, as well as increasing the photon energy reach. And in terms of capacity, currently we're kind of on this middle line here. There is room to actually construct additional tunnels and additional experimental halls, or actually to steer the beam into some existing buildings. And these unfortunately, or fortunately, would have to be limited to sort of soft X-ray wavelengths because of the limited undulator tunnel length you have leading up to these buildings. But this megahertz pulse train gives us the ability to actually fan the beam out to, for argument's sake, 10 sources, each running at 100 kilohertz if one wanted to. It really provides a real accelerator backbone, and we're mostly limited today, or will be with LCLS II actually, by the amount of average electron beam power we can dump into the electron dump. And we could keep that same value and kind of spread that out over four or five places. So we were requested by the Department of Energy sort of at the end of last year to develop a plan for LCLS II high energy, or HE. And so that's sort of these two bullet points. So filling out the first kilometer with cryo modules and looking at improving the gun emittance. So what does that do for us? Well, I just discussed LCLS II, and we kind of have a severe roll-off around 5 keV with LCLS II HE. That would really extend our operating parameters, again, all the way up to the selenium edge with pretty good performance. And these numbers are somewhat conservative. We're pretty sure we'll be able to hit those, and most, like LCLS I, exceed a lot of performance parameters. And with improved emittance, you get to this green curve. That would be really exciting. So the details involved with that, it's adding 19 cryo modules, extending what was done with LCLS II. Turns out we have enough cryogenic cooling capacity with the LCLS II project to support these additional cryo modules. And we also have some plans for kind of refurbishing the far hall, similar to what our plans are for doing with the near hall. And so that's LCLS II HE in a nutshell. And this was sort of the science slide that was shown to DOE BES. I'll also point out here, again, you don't see biology, but that's for a different reason. It's not because we don't think that source can have a big impact in biology. It's simply we were kind of tailoring the slide to our audience, which doesn't do so much biology. But certainly, I think doing serial crystallography at a 10 kilohertz repetition rate would have huge impacts. But the important thing here is at the bottom. So we're planning workshops. We're eyeballing sort of the mid-September timeframe, where we're going to try to assemble a detailed portfolio of science opportunities enabled by LCLS II HE. And we will have a biology session in those workshops. And so why?
Yeah, if they don't make any difference.
Well, I think this was, obviously it's not the thrust of basic energy sciences, but they're also sort of the stewards of these user facilities. And so they encourage, science to be done that might not be exactly in their wheelhouse, but they constantly are talking with DOE, DER, NIH, those sorts of facilities, and we even have a fusion energy sciences instrument at LCLS. So I think this was just a slide taken for a committee of materials scientists and chemists for.
So it would help you if we came to that.
Oh yeah, absolutely. In fact, more than help, we actually need strong advocates to make this happen. This is the time. We kind of passed the first litmus test, which there was a BSAC subcommittee meeting a couple weeks ago that kind of came out and prioritized the potential big user facility projects that were out there. And we kind of cleared that test. And so now, you know, it's if there's strong advocates for this, it could be realized in a relatively short time frame. Short for project perspectives.
Of course, the upper left panel is not irrelevant to biology.
True. Yes, good point. And again, just to come back to the users meeting, we're going to have an afternoon workshop at the users meeting as well. That's independent of the workshop we're going to have, the dedicated workshop we're going to have in September. Okay, so in summary, LCLS II construction is going strong. We have great partners that we're working with, and things seem to be on track. We're also designing new X-ray instruments to take advantage of this new source, and we anticipate first light in 2019 with user operations in 2020. And LCLS II HE, this 8 GeV extension, which would get us to the sort of angstrom wavelength range, is being proposed and considered. And as I just mentioned, you know, strong user community support is essential. We really need strong advocates to make this happen, and this is the next couple months are a critical time frame for that. Thank you for your attention.